Okay, so I'm floating out in space, and someone puts a force of 140 newtons on me. What happens? So there I am, and I know my mass is 70 kg. Someone puts a force on me of 140 newtons. What's going to happen? This is a dynamics. I got force, I know there's going to be acceleration, right? So I can say, yeah, F equals ma, acceleration equals force divided by mass is 140 newtons divided by 70 kg. A newton is a kilogram meter per second squared. Kilograms cancel, and I have 2 meters per second squared. I accelerate in this direction. Now, another person comes along and puts another rope on me with 140 newtons. What happens? And you say, oh, simple, right? I just double the force. That's going to double the acceleration. The acceleration is 4 meters per second squared. But what if that force is in this direction? Now we know what happens. Nothing, right? Except I get strangled maybe. But there's no acceleration because these two forces cancel out. So what we realize is force is a vector and must be added like vectors. We add vectors like this, nose to tail, and add it up, it gives me 0. So what we realize then is this formula is incorrect. It's not just a force gives you an acceleration. What we know instead, we have to take the sum. How? The vector sum, not the scalar sum. The vector sum of the forces acting on a body is equal to the mass of that body times the acceleration of that body. Here's another example. I have an apple. Is there a force acting on it? You say, well, yeah, force of gravity. Then how come it's not accelerating? Ah, right, because it's the vector sum of the forces that equal mass times acceleration. The acceleration is 0. The vector sum of the forces better be 0. So we do our first free body diagram. We have that mass sitting on my hand, and the force of gravity is pulling down. So there better be an equal and opposite force, because I know that the acceleration is 0, so the vector sum of the forces must be 0. And sure enough, we have my hand supporting this, such that the normal force pushing up plus the force of gravity pulling down is equal to 0. And sure enough, if I take away the normal force, it accelerates because the total force is just gravity. So this is a very interesting situation because I have gravity pulling down. Gravity is an attractive interaction whereby momentum is exchanged between the apple and one other body and the earth. That's gravity. The normal force is a repulsive interaction between my hand and the apple. Again, an exchange of momentum between my hand and the apple. They're equal and opposite. And so the acceleration is 0. Are they always going to be equal and opposite? Well, they're two different forces. One I can't control. It's a force of gravity. The force of my hand, I can control that. I can make that force much greater. And then the sum of the forces is this. And that's my net force upward. Or I can make it less. I could change the direction. Whereby now I have the force of gravity and the normal force is pushing down. I have a much larger net force in the downward direction, and so the acceleration is even more. So force is a vector, acceleration is a vector, they need to be added like vectors. So we have an idea how vectors come into play in dynamics, in forces. How about in the conservation of momentum? How about in the conservation of energy? And how about in kinematics? So for momentum, remember when I had a mass of 2m moving at a velocity of v0, and it collided with a mass of m0 moving with a velocity of 2v0. we calculated the momentum, and this one was 2 m naught v naught. Let's call this momentum 1 in this direction, and this was momentum 2 is 2 m naught v naught. These are equal and opposite momentum. They collided and stuck, and the final momentum was 0. The initial momentum was also 0 because we add these momenta like vectors. How different would that be from us saying this mass of m naught moving at 2 v naught collides with and sticks to this mass of 2 m naught moving at v naught? Where one is you have this going on, and here you would have this going on. So we pick an axis. We could say this is the positive x direction and know that that's the positive x direction. So this becomes a negative 2 m naught v naught in the x direction, and this is a positive 2 m naught v naught in the x direction. And we can see that these would add to 0, but here both of these have the same momentum. P1 is equal to P2 is equal to 2 m naught v naught in the negative x direction. So here, the sum of the momenta is 0. And at the end, it's not moving. But here, the vector sum of the momenta is equal to negative 4 m naught v naught in the x direction. And when they stick together, what do we have? You'd say this is P initial. And at the end, we have this mass that really is 3 m naught, everything stuck together, and its momentum is in this direction at 4 m naught v naught. And so what we'd say then, P final is equal to this mass, 3 m naught, times that final velocity. So what is that final velocity? I know that this momentum in the beginning must be equal to this momentum at the end. So we set them equal to each other. P naught is equal to P final, or negative 4 m naught v naught in the x direction is equal to 3 m naught v final. And we can see masses cancel, it's just a ratio thing. V final is equal to negative 4/3 v naught. So this one speeds up by 1/3 v naught, and this one slows down. If we write the initial speeds as 3/3 v naught and 6/3 v naught, we can see that this one speeds up by 1/3 v naught and this one slows down by 2/3 v naught. Or maybe what's most important is this gets an impulse in this direction of 2/3 m naught v naught. So delta P on this guy speeds it up at 2/3 m naught v naught. And this one slows down. Delta P is equal to negative 2/3 m naught v naught. And if I were to be completely correct, this is a vector. This is a vector, and this is in the negative x direction. And this is a vector, it is in the positive x direction. And so we can see that the two impulses that these guys get are equal and opposite, and there is no net change of momentum.